Well guys, as you guys know that the electrical package has been launched and feedbacks have been really positive from all the corners, whether a marine engineering student, whether a GME aspirant, whether a person is going to join a ship for the first time, a ETU aspirant, and even some electrical engineers have bought the package. Some electrical officers have bought the package as well. This electrical package starts from electrons to atoms to current to voltage to resistance to capacitance to inductance. That is how this basic electrical package has been started. I know all you guys, just for an example, you know about Faraday's law of electromagnetic induction, right? You guys have studied on YouTube, on books, but this is one of the most important laws. So in this coming video, you will see how Arvind Singh sir explains this very basic thing. So guys, this is just a sample. Again, every week we'll be putting some or the other videos just to share with you how this package works. Let's learn together, let's grow together, and let's make this maritime community proud, keeping our respect on shipping intact.
Hey guys, welcome back. In this module, we are going to discuss about how can we create magnetic effect to electricity. Previously, what they did, that you know already, that in previous module we have discussed how to create magnetism out of electricity. That means electrical energy to magnetic energy, and we made electromagnets to do that. Now scientists started discussing among each other that is the reverse also possible? That means, okay, we converted electricity to magnetic field. What if we can convert magnetic field to electricity? That would be so nice. That means if we have magnetism with us, we can convert that to electricity. So we can generate electricity out of it, right? So let's see how we can do that. The principle with which we can do this is called electromagnetic induction. And what are the famous laws regarding electromagnetic induction? Yes, Faraday's law of electromagnetic induction. So Mr. Faraday demonstrated that yes, it can be created and to convert magnetic effect to electricity, and he gave two laws for that. So let us study those famous two laws of electromagnetic inductions. First law, it says that, first of all, let's see the picture, what is happening here. So there is a coil, let's say only one loop, only one turn, and there is a magnet, there is some field is passing through the coil. From where the field is coming, I really do not care about that, but there is a field through the coil. This we called as flux linked to the coil. Flux linked. So it is linked. Linked means whatever flux is inside the coil, that is flux linked. If you say that this is also flux present in the vicinity, but this time it is not linked because it is passing outside the coil. So we are only focusing on this flux that is inside the coil, right? So if the value of flux inside the coil or the flux linked to the coil changes, if this flux changes, that is inside the coil, then there will be EMF generated at the terminal. This is what the first law says. So change of magnetic flux linked to a coil induce an EMF across the coil. The EMF has been induced. EMF, or you can say potential difference. This has been induced. Isn't it a magic? So a magic happened. When the flux linked to the coil changes, terminals will experience some potential difference. That's what first law says. Forget about the magnet for the time being. This flux could be coming from anywhere. Law 2. The EMF induced, which EMF? The one which you are talking about in the first law. The same EMF that is induced across the coil is equal to the rate of change of flux in the coil. So first law tells us there will be EMF induced. Second law is telling us the value of EMF. That means the formula means it is quantifying it. How much is the EMF being produced? Is there any relationship between EMF produced and how fast my flux is changing? So there you can see it's equal only, means the rate of change of flux. In my previous module we have already studied what flux is. The total number of field lines passing through the area is flux. If they are changing, then it will induce an EMF, and that EMF is nothing but EMF is equal to minus d phi by dt, means rate of change of flux. This negative sign will simply tell us that the EMF induced will simply oppose the rate of change. So if you are increasing the flux, EMF will be in such a direction that it will oppose the increase. If this is decreasing, EMF will try to oppose the decrease also. So the sign will always remain negative. So you can pause the video and just remember the definition here. Okay, one more thing. The flux in this case, I am using a permanent magnet to create this flux. This could be an electromagnet also. So this is out of question, right? This could be electromagnet or permanent magnet, doesn't really matter. What matters is there's a flux. Okay, moving on. Now the same picture you can see here. There's a coil, there's a source of a flux that is producing flux, that is linking to the coil, and if I am changing the flux, there will be EMF induced, and if I close the circuit, that EMF will drive some current which I am measuring through ammeter. I can use a voltmeter also. So here the voltmeter will show me voltage instead of current, right? Okay, formula is same. E is equal to, in this case I am using N, because in my previous case I had only one turn, so N was 1. So this flux was because of rate of change of flux is because of one coil. When you have N number of coils, then you are multiplying by N, because yes, makes sense. No? This one coil is this part, N number of coils, more the number of coils will be there, more will be the EMF produced, and that is why you would want to have more and more turns just to have more and more EMF generated there. Okay, now we also, in my previous module, we discussed what is the formula of flux. If you remember, flux is nothing but B dot A or BA cos theta, where BA cos theta means this theta is angle between field and area. Field, so this is the field, you can see this is the B, and area is the area of this coil, the cross section of area of this coil. So if I see here rate of change of flux, that means I differentiate this part d phi by dt. So I differentiate this also, that is d this thing by dt. So that means either I can change B, field strength, or I can change the area, or I can change the angle between them. In all of those cases, I will have a EMF induced. So let's take one by one. How can I change the field strength? How can I change the field strength through this coil? I can bring the magnet farther or closer. So taking the magnet like close and farther, it is going to produce EMF. Number one. Changing the area is difficult. I can't change the area of this coil, so that is out of question. Let's talk about the angle. So can I change the angle between field and the coil? Yes, I can. If this is a magnet, I just simply rotate the magnet. So when I rotate the magnet, I can change the angle between this thing. So if I rotate my magnet, I will have an EMF induced. And gentlemen, those who know, they would have understood by now, this is the principle of AC generator. In AC generator, you have a magnet. You have a magnet having fixed north and south, and you're rotating a magnet inside a coil. So near to a coil, if you rotate a magnet, this will produce a single phase. In this case, it is producing a single phase AC. So this becomes a, because EMF is generated here, that means it becomes a, and that's a generator. It generates, so it gives an output, voltage output. So this is giving a voltage output. So you can use electromagnetic induction principle to make a generator, right? Okay, one more thing. Had this not being a permanent magnet, let's say I take an electromagnet instead of permanent magnet. So this is an electromagnet, plus and minus. So in this case, I can either rotate this magnet, and this will also do this. This will also produce EMF, or I can keep my magnet still and I can rotate this part. In both the cases, there is a relative motion, isn't it? And then again also there will be EMF induced. Or I can do one more thing. Instead of AC, instead of DC, if I start giving AC here, see what happens. If I give AC here, what is current in this line? Is it fixed? No. The current is changing like a sine wave. So when current is changing, who is producing field in this coil? It's the current. If my current is AC, sinusoidal wave, then my flux also will be sinusoidal. Flux will also change alternately, isn't it? If there is no current, this will be 0. If current this side, it will become north. If current the other side, it becomes south. So my flux is changing just by giving AC here. So that, will this induce EMF here? Yes, of course, because my flux is changing. And what does it look like? Two fixed coil. Inside one I'm giving AC and I'm getting AC output. So does it ring a bell? Yes. It becomes a transformer then. So this is a transformer principle where I've got two coils where I'm producing a changing magnetic field in one and pushing those changing magnetic field in another one and getting an output in another coil. So this becomes my single phase transformer. So there's so many application of electromagnetic induction. We are going to discuss these things in details in the future section, but just to prepare a ground that where it all comes from. It all comes from this thing where flux is nothing but BA cos theta. You change something and you get something. You get an EMF, right? Okay. So you can pause the video and just see what we have just discussed. It's same thing written here, right? That's all for this video, gentlemen. We'll see you again with further explanation of the same thing. Thank you so much.